Hi friends, this class is about the extension of the gas turbine. So generally gas turbine works on the Brayton cycle. So in this class we are going to discuss about this thermodynamic cycle for the gas turbine engine. So gas turbine engine mainly works on Brayton cycle. So this is also called a Joule cycle. Okay. So in the Brayton cycle, how the arrangement? So this is the jet, that means a gas turbine. So either it is a open gas turbine or a close to gas turbine. In both the cases, we are using Brayton cycle only. So for the simple or closed gas turbine, let us see the PV diagram, and then so that we can understand it better. So in the case of PV diagram, we just have a different process. So here, this let us take this is 1, and it is 2, and it is 3, and it is 4. So from 1 to 2, it is generally we call it as isentropic compression. So this is to be like this, and then from 2 to 3, it is constant pressure heat addition. So we just have such kind of this, and from 3 to 4, it is isentropic expansion. So this is, and then from 4 to 1, it is so here it is open. So if it is a closed cycle, we have this. So it will be connected, and that is also constant pressure heat rejection. So here it is the direction. So that is we have this and like this, and then this. So it is, this is what, okay, we need to just note down, and our heat addition. So that means heat is applied to the system here. So heat is supplied. So here what our heat is supplied. So this is nothing but Q in. So and then similarly here it will be Q out. Yes, and then yes, this is, so this is what about what to say, Brayton cycle, PV diagram, and that means pressure volume diagram, and these are the four process. So we have a constant, that means constant pressure process for the heat addition and heat rejection, and isentropic compression for the compressor, isentropic expansion for the turbine. So if you want to denote, this is nothing but compressor, and here it is a combustion chamber, and here we have a turbine, and here it is nothing but intercooler. So if it is a closed one, here it will be a cooler. So this is, and if it is open, this, so it won't be connected. So that is the idea. So okay, so let us see the that means we have seen the different process, and how to find out uh, the efficiency for the gas Brayton cycle, and is so that is applicable for simple gas turbine, also closed gas turbine cycle. So this is efficiency we need to calculate based on the heat supplied and heat rejection. So nothing but so we just let us see the efficiency formula for this case. So our efficiency is nothing but for the gas turbine is nothing but we just, or okay, based on the Brayton cycle we define it like this. So net work output, net work output divided by heat supplied. So that means heat supplied, nothing but a heat in. So the network output, we just say it is nothing but Q in minus Q out. So this is divided by Q in. So this is further simplified, becomes 1 minus Q out by Q in. So this is what efficiency. So we need to understand what is meant by Q out and Q in. So based on our previous diagram, so we can write Q in is nothing but that is the enthalpy change. So based on the enthalpy change, we can write Cp into T2 minus T1. So that is a actually it is a Q in. So it is between the temperature. That means states between 2 and 3. So it should be T3 minus T2. So and then Q out, it is between the state 4 and 1. So it is T4 minus T1. So this is. So if you substitute this and then this equation further reduces. So we can just write. So our efficiency formula becomes eta equal to 1 minus Q out by Q in. So this Q out is nothing but 1 minus, we have written this as Cp into T4 minus T1 divided by Cp into T3 minus T2. So here we can cancel out this Cp. So remaining will be 1 minus T4. So from here let us take T1 outside, and from the denominator let us take a T2 outside. So from the numerator I am taking T1 outside, it becomes T4 by T1 minus 1 divided by T2. Here we are taking T2 outside, so it is T3 by T2 minus 1. So this is a further simplification, and then now again we need to simplify this further. And if you see the PV diagram, from the PV diagram, so we can understand that so from PV diagram, so we can understand that P3 will be equal to P2 because that is a constant pressure process. So the pressure remains constant between the state 3 and 2. So that is why P3 equal to P2, and our P4 will be equal to P1. So between the state 4 and 1, the constant pressure process. So again the pressure remains constant. So that is the reason. So P4 equal to P1. So this is we need to note down. And then for the isentropic compression, we can write. So isentropic compression happens between states 1 and 2. So that we can write T2 by P1 equal to P2 by P1 whole power gamma minus 1 by gamma. So this relationship is given by adiabatic process. So because isentropic is nothing but process is adiabatic and also reversible. So that is the thing we need to understand. So this is the relationship between pressure and temperature given by adiabatic process. Similarly, this is for isentropic compression. Similarly, we can write it for isentropic expansion. So nothing but that is happens between 3 and 4. So T3 by T4 equal to P3 by P4 whole power gamma minus 1 by gamma. So this is we need to further simplify. How we are simplifying this? Let us see. So our this one T3 by T4 we have written is as P3 by P4 whole power gamma minus 1 by gamma. So and also we have noted P3 is nothing but P2. So this further can be simplified as a P2 by P4 is nothing but P1. So we can replace P2 by P4 P1 whole power gamma minus 1 by gamma. So now we got a T3 by T4 equal to this. And this is also equal to, we have seen that T2 by T1. So from this we can write T3 by T4 equal to P3 by, that means T2 by T1. So this further can be rearranged. That is nothing but T3 by T2 equal to T4 by T1. So this is, so this relationship we can substitute in the efficiency formula, because our efficiency formula says 1 minus, we have taken T1 in outside, T4 by T1 minus 1 divided by T2 into T4 3 by T2 minus 1. So if you substitute this relationship in this formula, then the efficiency becomes, that means these two will get cancelled. So if you substitute this and these two will be cancelled out, then remaining will be, so this. So our efficiency becomes eta equal to 1 minus T1 by T2. So and then this is further can be modified 1 minus 1 by T2 by T1. So we know T2 by T1 is what in terms of pressure. So we are writing, replacing 1 by P2 by P1 whole power gamma minus 1 by gamma. So and we can say that P2 by P1 is nothing but pressure ratio. So P2 by P1 is nothing but we say RP. So that is we call it as pressure ratio. So this is then again we can replace our efficiency further becomes 1 minus 1 by Rp power gamma minus 1 by gamma. So this is the formula for finding the efficiency of the gas turbine engine. So we can say for the simple gas turbine engine, this is the formula. So this can be applied for the simple gas or closed gas turbine as well as for the open gas turbine.